Hello. Let's talk about another behavior of waves, this time interference and consequence of interference, beats. When wave pulses meet in space, they would interact and interfere with each other. That doesn't mean that they destroy the wave or destroy the energy. Again, energy cannot be created nor destroyed, but it can be screwed with a little bit. So when waves interfere, they can change the amplitude of the pulse of the wave at that location, but overall they don't permanently alter the wave. Once the interference is done with, the wave returns back to normal. Imagine you're talking about a water wave, just basically droplets of rain hitting a surface of water. As the droplet hits the water, it will cause a pulse to be sent outwards. That pulse will interact with other pulses. Basically, you'll get a pattern like I'm showing on the screen here. But notice that the rings are still intact, even though they've run across each other. So they will interact, they will interfere with each other. That will cause some areas to be higher, some areas to be lower. It'll change their amplitude, but overall, the ring structure remains intact. There are two main types of interference, constructive and destructive. Constructive interference happens when you have crests line up and troughs line up. So when a trough lines up with a trough, or a crest lines up with a crest, trough and trough, crest and crest, you'll get a larger amplitude. Constructive interference is where you would add amplitudes. These waves are in phase because they line up. Destructive interference is where you subtract. So the crest and the trough are matched up, and the crest and the trough are matched up here. They are completely out of phase. In that case, they would interfere with each other by subtracting the amplitudes. So when crests line up, it's constructive. When it's crest with trough, it's destructive. Constructive you add, destructive you subtract. Notice that every time a crest lines up with a crest, you get an increase in amplitude. And when a crest lines up with a trough, you get a decrease in amplitude. Now, for the examples I've given so far, they have the same amplitude. They are pretty much identical waves. So destructive interference in this case would produce a zero amplitude. However, that is not always the case. That is only if both waves would have equal but opposite amplitudes. It is essentially a vector. Vectors only cancel if they are equal and opposite. Now, this kind of technology can be used in a lot of different ways, but one of the ways that you might be familiar with it is noise-canceling headphones. Noise-canceling headphones don't actually cancel out the sound. It can't. Sound is a wave. Waves are energy. You can't destroy energy. But what it can do is produce its own sound wave, basically the same sound, but out of phase with the original sound. When it does that, it interferes with it, removing that amplitude, basically causing you not to really hear the sound. That only tends to work if the sound is relatively repeated. If you have a person talking to you, since the sound varies so much, it is very hard for the headphones to keep up with. So that tends to be why if you're listening to, say, noise-canceling headphones while running a jackhammer, you can still relatively hear people talking to you. The constant noise of the jackhammer can be canceled out, whereas the unique noises caused by speaking can't be easily adapted to very quickly, and you can more often hear them than just background noise. One of the other interesting ways that this worked is scientists have developed a way to essentially make standing waves of sound. Now, the sound might be used as infrasonic or ultrasonic. It's out of the range of human hearing. But let's say you wanted to look at some medicine that you didn't want to touch a surface because it would evaporate very quickly. By suspending it in a sound field, places where there would be destructive interference, the particles, the droplets, could be suspended in air. You might more commonly be used to interference with the idea of, say, a stereo system. A stereo system would be a two-point source interference pattern. If you had two sources giving off sound waves of the exact same sound at the exact same time, they would interfere, but it would cause an interference pattern. Certain areas would be greater pressure, crests. Certain areas would be lower pressure, troughs. When they interact, you would get areas which are basically going to be louder or quieter. The picture on the right here, I have two needles making waves in water waves, and you can see that there are areas which are brighter and that are darker. The brighter areas being crests, the darker areas being troughs. And the waves tend to have a pattern there. They travel away from the center in kind of a line. So you can see that we have areas of lines going away from the source. This goes along with the idea of the study of acoustics. When you try to create something like a concert hall, you'd want to put people in the areas where you would get a lot of sound. That's where you put your seats. Areas where there is very quiet, maybe that's where you put your aisles. If you were to set up a stereo system at home, a lot of times home stereo systems would come with instructions on where to place your speakers in what direction and where you should sit. So if you were going to put a home stereo system together, it might say put the back speakers at a certain angle in a certain direction. The idea being, when it hits your spot in the center of the couch here, it's all constructive interference and it would sound louder. If, however, you were to sit somewhere that was slightly different from it, you might sit in a place that is destructive interference and would be less amenable to listening to things. If you do have a home stereo system, try that one time. Produce a sound. It's good if it's the same sound repeated. And just walk around. See if you can find areas that are louder and areas that are quieter. The areas that are louder have constructive interference. The areas that are quieter have destructive interference. So once again, constructive interference is adding amplitudes. Destructive interference is subtracting amplitudes. The picture on the left is constructive. The picture on the right is destructive. But after they have interfered, they will keep going their same way they were before. So in the spot in the middle here, they will combine. If you're sitting in that middle spot, you will hear a louder sound. But afterwards, they will separate and go back to what they originally were. So let's say you have two people arguing with each other. If you stood in between them, it would sound louder to you because they are interfering and being really, really loud. However, you know that they interfere in between them, but if you were behind one of the people, you would still hear both voices distinctly. You would still hear the sound of the person talking towards you because that wave is not destroyed, it's just combined for an instant. So waves are interfered with for an instant, but not permanently altered. And interference does not have to have the same amplitude. So if you have here a case of constructive interference, the waves do not have to have the same amplitude. Any waves will interfere with each other. Now, one of the things you might be more familiar with is the idea of a beat frequency. So this would occur if you have two waves that are interfering that are not exactly the same frequency. A beat frequency would be the difference in frequencies between waves when they undergo interference. This would be something like if you were at a stoplight and you had your turn signal on, and the car in front of you also has their turn signal on. you might notice that every now and then the clicks you hear for your turn signal match up with them, but then they slightly get out of sync. So every now and then they're in sync with you. Their blanks match up with your clicks. Give it a few seconds, and then all of a sudden, they're out of sync. They're the exact opposite of yours. So with a beat frequency, there are areas where there is going to be constructive interference when they do match up, and there are going to be areas where there's destructive interference where they don't match up. Very quickly, to calculate the beat frequency is pretty simple. A beat frequency is simply the difference in frequencies between waves. If I have a wave that is 40 hertz and a wave that is 50 hertz, my beat frequency would be 10, the difference between the waves. So as you have a beat frequency, certain areas are going to be in phase, that would be the constructive interference, and certain areas will be out of phase, that would be the destructive interference. So listen for the sound right here. If I now have a beat frequency of 1, you might hear the sound rise and fall once per second. A beat frequency of 2 would mean the sound would rise twice a second. So when you have a beat frequency, it is the difference between the frequencies. In this case, 500, 503 would mean a beat frequency of 3, or it would rise and fall 3 times a second. At some point, it becomes hard for the human ear to hear. And sounds pretty much like background noise. So beat frequencies happen when they are slightly out of sync. You get areas of constructive interference, you get areas of destructive interference. The ear then would interpret that as a rise and fall a certain number of times per second. Okay, I'd like you to consider this question here. Looking at the picture, what type of interference do you think would be shown here? And when they do interfere, what do you think would be the resultant amplitude? Go ahead and pause the video, consider your answers. Well, we're showing both crests here. They are moved towards each other, they're both crests, which means it would be constructive interference. There would add their amplitudes. Because each amplitude is x, that means the interference pattern would have an amplitude of 2x, or twice as much. Well, what about this one? What type of interference would be shown here? We have a wave or pulse of -5 heading to the right and a pulse of 3 heading to the left. When they interfere, what type of interference would it be, and what do you think the resultant amplitude would be? Take a second, go ahead and pause the video and consider your answer. Well, because we have a crest and a trough, that would mean destructive interference. They would end up subtracting. And the difference between the two is -2. So in this case, the resulting interference would be -2. Wouldn't be 0 because they're not exactly opposite of each other. They're not exactly equal of each other, but it would be opposite. +3 - 5 ends up being -2.